So last time we started our discussion of solids and liquids, and we decided that we were going to break down all the solids that exist naturally into three categories based upon whether the solid is composed on the microscopic level of millions and millions of ions, millions and millions of atoms, or millions and millions of molecules. And if you have matter that's composed of millions and millions of ions, that is always an ionic substance. It would be a metal-nonmetal combination: sodium chloride, magnesium bromide, calcium sulfate. So these are called ionic solids because they exist in an array of millions and millions of positive and negative ions that are attracting to each other with an attractive force called an ionic bond. Ionic bonds hold ions together. When you have a crystal like that, because the ionic bonds are so strong, they actually are held together so tightly, it takes a lot of energy to melt them. So we talked about how yesterday, all ionic crystals like salt or magnesium bromide or calcium sulfate have really high melting points. You have to heat them to 800 degrees before you can break the ions apart from each other and allow them to roll around and be a liquid. So that was ionic matter. You can also have matter that's not composed of ions, but it's composed of atoms. And it's important that you understand the difference when we say atoms or ions. Ions mean charged particles. If you say atoms, you really mean neutral particles. And sometimes we say, oh, that atom of a sodium ion. That doesn't make any sense. Sodium ions are ions. Atoms are neutral. So sodium atoms have no charge. Iron atoms have no charge. Oxygen atoms have no charge. So sometimes we can have solids that are just an array of millions and millions and millions of atoms. And there's actually three different types of solids that can be made of atoms. The first type are metallic crystals or metallic solids. These are made up of millions and millions of metal atoms like iron, like gold, like copper. And what holds them together, because they're actually bonded, is they're held together by having the metals shed their valence electrons. The valence electrons migrate around the entire metal crystal, and those negative electrons attract all the positive nuclei of all the metal atoms, and that's what holds the metal together. That's called a metallic bond. So metals are held together with metallic bonds, which are really, really strong, and so therefore we expect metals to have really high melting points, like 1,000 or 2,000. So both ionic matter and metallic matter, ionic matter made of ions, high melting point because ionic bonds are really strong. Metallic matter, which is made up of metal atoms, has a high melting point also because the attractive force between the metal atoms are metallic bonds. And at the end of yesterday, we introduced one other type of substance that exists as millions and millions of atoms that are all bonded together. That was called macromolecular matter. And there's only a very few number of examples of this that actually exist that are common, but they're mostly made up of the elements that are in the nonmetal part of the periodic table in columns 13 and 14. Boron, carbon, and silicon. Especially the elemental forms of those. What is a sample of boron? It's actually millions and millions of boron atoms that they're technically all bonded together. And how do nonmetal atoms bond? With covalent bonds. So a crystal of boron is millions and millions of atoms that are all covalently bonded together. That actually means a crystal of boron is one giant molecule, thus the name macromolecular. A diamond is millions and millions of carbon atoms, all covalently bonded. A diamond is one giant molecule. These are called macromolecular substances, and because they're held together by covalent bonds, which are just as strong as metallic or ionic bonds, macromolecular substances like diamond have really, really high melting points. So yesterday we talked about these first three categories of matter, and the similarity between the three is they all have very high melting points. They're solids at room temperature, and you have to heat them up to like 1,000 degrees or more to actually make them melt into a liquid. We're going to talk about the last three categories today, and we're going to talk about one more category of matter that exists only as atoms, but it's a little bit different than the metallic or the macromolecular because they're going to be non-bonded to each other, and that's what noble gases are. So noble gases would be any matter that's composed of noble gas atoms. And examples would be, we'll just go to the noble gas column on the periodic table. It's column 18. Helium, neon, argon, krypton, xenon, radon. These are all the noble gases on the periodic table. The nonmetals are located on the right side. The noble gases are the final column. So if you have a sample of any of these and you cool them down low enough to make them into a solid, and it might take like negative 200 degrees to do that, you can make a solid, and that solid would be an array of millions and millions of noble gas atoms. Each individual point in that crystal is a noble gas atom. But here's what's different between this and then the ionic, metallic, and macromolecular substances we saw yesterday. The ionic substances, those particles attract each other with ionic bonds. In a metal, those particles attract each other with metallic bonds. In a macromolecular substance, those atoms attract each other with covalent bonds. But in a noble gas, these atoms are not bonded to each other. So what's holding them together? That's a really interesting question. We know there has to be something holding them together, because if we cool down neon or argon or krypton or helium, it'll become a solid. We can make a crystal of it. And the only way you can make a crystal is if somehow they're attracting each other. But they're not doing it by one of the 3 types of chemical bonds that we learned in Unit 2, which will be on the first page of your test, no doubt, next week. They're attracted by something else. It must be some more feeble, weak attractive force that we're going to learn about today. So this attractive force between those noble gas atoms in a crystal of a noble gas is not covalent bonds. That's important for you to understand, okay? The atoms do not chemically bond together. There's no ionic bonds, there's no metallic bonds, and they're nonmetals. So there's actually, you would guess, covalent bonds, but it's not that. They bond together with something different. They bond together with a really weak attractive force that has now become known as a London dispersion force. What is that? We don't know yet. We'll talk about in a couple of minutes. But let me first just introduce all the properties of noble gases I would like you to know, and then we'll go back and try to explain what this brand new attractive force is. Now, this London dispersion force is actually going to be really, really weak. It's way weaker than ionic bonds, way weaker than metallic bonds, way weaker than covalent bonds. So if it's a really weak attractive force, the atoms do not hold together very strongly. What does that mean? That means it's easy to separate them. It's easy to melt them or boil them. So they melt and boil at really low temperatures. That's because the London dispersion forces are really weak. Their typical energy is something like 1/10 of a kilojoule per mole. So think back yesterday, the covalent bonds, ionic bonds, and metallic bonds were like 400 kilojoules per mole. So the London dispersion force is only 1/4000th as strong as a typical chemical bond. That's such a weak attractive force, it'd be easy to have these noble gas atoms separate from each other and therefore melt into a liquid or boil into a gas, okay? In terms of water solubility, noble gases do not dissolve very well in water. That's because water, if you remember from yesterday, is a polar substance. It has positive and negative ends. So it will attract something and dissolve it if the other substance has positive and negative ends. But what are noble gases made up of? They're made up of atoms which are neutral. An atom doesn't have a positive end or a negative end, so the water has nothing to attract to it. So therefore, there's no real attraction between these non-metal atoms of the noble gases and the polar water molecules, so they do not dissolve in water very well, okay? In terms of electrical conductivity, the electrical conductivity of a material is always due to the fact that charged particles can move through it. Charged particles are either ions or electrons, and noble gases aren't made of ions, and the electrons on a noble gas atom are stuck on that atom. So they don't move from one atom to another. So there's no ions that are existing that could move, and there's no electrons that can move. So therefore, a crystal of a noble gas or a liquid noble gas or a gaseous noble gas would not be able to conduct. There are no mobile charged particles, okay? So I would like you to understand these properties of noble gases. So now let's go back and talk about what this mysterious London dispersion force is. There's got to be some reason that noble gas atoms attract each other. We know they have to, otherwise they would not be able to form a solid. And in all reality, chemists hundreds of years ago were going, well, I don't think there is any attractive force, so I bet we can't make solid argon or solid lithium or solid neon. And then somebody did it and they go, okay, well, that theory was wrong. There has to be some attractive forces between it. What could they be? Well, if we take a look at a couple of helium atom has a nucleus with 2 protons, and it has a 1s orbital with a pair of electrons in it. So let me draw the nuclei here. So those are the positive components for the helium atoms. And then the 1s orbitals, which are in that sort of a maroon color, that has the negative electrons in it. Okay. Ms. Eckes asks a question, if noble gas don't conduct electricity, then how do neon signs work? So Ms. Eckes, I'm going to take you back to experiment 3 that you had to visualize online because we couldn't do it in person, where we actually passed electricity through a hydrogen gas tube. And what did the hydrogen gas tube do? It glowed. So why did that happen? The electricity you pass through hydrogen gas just causes the electrons in the hydrogen to jump to higher energy levels. It didn't cause the electrons to move anywhere. They just jumped from low energy levels to high energy levels. And when they dropped back down, they emitted specific photons of light because the electrons can only be certain distances from the nucleus. And so certain wavelengths were given off, and the hydrogen glowed a characteristic lavender color. All right. If you put helium gas in a tube and pass electricity through it, you're not making the electrons in one helium atom move to another. You're just making the electrons go from low orbits to high orbits or orbitals. And then when they drop back down, they emit specific photons of light. Helium happens to emit photons of red, orange, and yellow. And when you combine those together, it looks orange. So passing electricity through neon doesn't make neon conduct electricity. That's not what's happening. You're just exciting the electrons. They're dropping back down and giving off specific wavelengths. So if you ever see a neon sign and it's orange, that's because it actually has neon in it. If you ever see a neon sign that's lavender, that's not a neon light. That's a hydrogen light, because hydrogen is what gives off lavender. And if you ever see a neon light that's pink, that's not a neon light, that's a helium light, because helium, when the electrons are excited and drop back down, give off a characteristic pink color. And if you see a blue neon light, it's not a neon light, it's a mercury light, because mercury vapor, when it gets excited and the electrons drop back down, they give off a blue color. Argon does the same thing, so it might be argon instead of helium, instead of mercury. But Ms. Eckes, is that okay? Good, okay, that's the explanation of those. So if we take a couple of helium atoms and we move these helium atoms together, and we think about what would happen, the first thing that should happen is actually the electron clouds, the maroon color here, are getting close to each other, and electrons are negative. These two electron clouds approaching each other should probably repel. And so our first inclination would be, I don't think these two atoms are going to attract each other. I think they're going to repel. Well, something kind of funky happens that you wouldn't have thought about. But as they approach, the electron clouds do repel. And what they do is they actually cause the electrons in one of the two atoms to be pushed backwards. And when the electron cloud moves, it doesn't take the nucleus with it. So the electron cloud in one atom will repel the electron cloud in a neighboring atom, and it's going to cause its electron cloud to shift so the nucleus is no longer in the center of the atom. It therefore causes the atom to have a positive end and a negative end. So watch as I animate this. As these clouds repel each other, one of the clouds is going to be repelled away, and it's going to go like this. And all of a sudden, the atom on the right now is no longer perfectly symmetrical in terms of its charge. The one on the left is perfectly symmetrical, positive in the middle, equal negative all around it. But as soon as the electron cloud on my right atom got repelled and it shifted over, we now have a negative end to the atom where the electrons are mostly located, and a positive side where the nucleus is. You have polarized this atom. It now has a positive end and negative end. Kind of interesting. Now that this atom has a positive end, guess what the positive end of that atom is going to do to this electron cloud? It's going to pull it towards it. It's going to polarize the first atom. So the positive end of our second atom attracts the electron cloud in the first, and watch the animation, it polarizes it. So this other atom now has a positive end and a negative end. So what you've done is you've created a pair of atoms that used to be perfectly nonpolar because the nucleus and the electron cloud was perfectly symmetrical. You've now shifted the electron clouds and you've now made them polar. We say they each now have dipole moments, much like a polar bond has. but they're not permanent, they're temporary just because they're caused by the influence of a neighboring atom. So this creates what we call temporary dipole moments, and the positive end of our second atom is going to naturally attract the negative end of the first, and that little attraction there is very weak, but it does exist, and it's called a London dispersion force. So the London dispersion force, and in some older texts, and I believe even on the MCAT they still call it this, they're called van der Waals forces. The London dispersion force is the attraction caused by the polarization of the electron clouds in neighboring molecules. That's what the picture's showing. The electron clouds have both been shifted, so now the electron clouds are polarized. They have a positive end to them and a negative end. What does this do? This creates instantaneous dipole moments. Sometimes we just say that called temporary dipole moments, but you can say temporary or instantaneous. And this results in the temporary positive end of one atom attracting the temporary negative end of the other. And you have a London dispersion force. As long as the atoms are close to each other, they stay polarized. If the atoms move apart, the electron clouds go back to perfect symmetry, the atoms are no longer polarized, they don't attract each other. So it only happens when these noble gas atoms approach each other. That's when the electron cloud, which used to be perfectly symmetrical, gets pushed over on each atom. So each atom will now have a positive end and a negative end that can naturally attract each other. So this is the way that noble gases can actually create liquids or solids. If you lower their kinetic energy down to a really low amount, which only happens at really, really low temperatures, then these really weak London dispersion forces can now overcome the kinetic energy and hold the atoms together as a liquid or even as a solid. Okay, so that's the major attractive force that exists in matter composed of only noble gases. So we've talked about matter that is composed of ions, matter that's composed of atoms. The only other thing we're going to talk about is matter that's composed of molecules. And what's a molecule? It's a group of nonmetal atoms that are covalently bonded together. So what if you have a sample that's made up of millions and millions of molecules? How can we describe what they're going to be like? Well, first, it's going to depend upon what type of molecules there are. Are they polar molecules or are they nonpolar molecules? Because they actually behave differently. So let's talk about nonpolar molecules first, okay? So a nonpolar molecular substance is any matter that's composed of millions and millions of nonpolar molecules. Now, when we use the word molecule, it infers only nonmetals, and it's groups of nonmetal atoms that are bonding together covalently to create a little unit where all the atoms get either octets or duets in most cases. So if you look at examples of nonpolar molecules, they're always going to be made of nonmetals. There's a couple that are really easy to recognize as being nonpolar, and let me show you them. First, if you have something like O2 or S8 or P4, these elemental nonmetals that each form molecules, these are automatically nonpolar. Do you have any idea why these three would absolutely be nonpolar and I wouldn't have to draw a Lewis structure or draw a shape and draw the dipole moments and see if they cancel out? I would just know they're nonpolar just by looking at their formula. Why would that be?
Every atom within its molecule has the exact same electronegativity.
That is so perfect. Mr. DiFilippo, the basic concept here, if you have a bond between oxygens, their electronegativities are the same. What's the difference? Zero. If the electronegativity difference is zero, the bond isn't polar. An O2 molecule doesn't have a polar bond in it. There's no dipole moment arrows. An S8 molecule cannot have a polar bond in it. There's no dipole moment arrows. So if there's no dipole moment arrows, it's got to be a nonpolar molecule. Perfect. So if you have any elemental nonmetals that create little molecules, they've got to be nonpolar. So there's got to be the elements over here, okay? Now, we've already talked about the boron, which is here, and carbon and silicon. They do not form molecules. They do not form molecular matter. They form macromolecular matter. So we're not going to talk about these. They don't fit into this category. We're not going to talk about the noble gases. They don't fit into this category. They don't make molecules. They just exist as atoms. It's all the other ones here. All these nonmetals, when they're in their elemental state, it could be elemental sulfur, elemental nitrogen, elemental chlorine, I don't care which one it is, they exist as little unique molecules that you can draw a Lewis structure for. And in fact, we've learned what many of them are. We talked about in our first unit that nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and plus hydrogen, always form diatomic molecules. So any sample of those elements are millions and millions of diatomic molecules. So they're going to fit into this category of nonpolar molecular. You're going to, especially for next unit, need to know what elements form diatomic molecules. There are 7 of them. Look what they're forming right here. Look at this. You see this? This is kind of impressive. What's that look like to you? Take your time. What's that look like? Are you imaginative?
Like a 7?
Oh, and there's 7 of them. Isn't it ironic how that works like that? But that's not all 7, right? 1, 2, 3, 4, 5, 6. The last one's way over there on the left side. Mr. Shams, if you go out at nighttime and look at the Big Dipper and look at the 2 stars on the edge of the Big Dipper and follow it up, do you know what it points at?
Not really, no.
Oh, does anybody know? Anybody know a little astronomy? What's the edge of the Big Dipper point to? If you were a navigator back in the 1500s, you know the answer to that for sure. It points to the North Star, Miss Eckes, the master sailor in the class. So look at this 7. Look what the 7 points to. The 7th diatomic element. Coincidence? I don't think so. How about that, huh? So those are the 7 diatomic nonmetals. All the other nonmetals in this group, they form molecules as well. It's just there are different number of atoms that make the molecule. Phosphorus and arsenic take 4 atoms to make their molecule. Sulfur, selenium, and tellurium all make 8. But every single one of these nonmetals, when they exist, don't exist as atoms. Boron, carbon, and silicon make macromolecular crystals. All the other ones make little molecules, so they're all going to fit into this category of nonpolar molecular. Here's something else that forms nonpolar molecules. I don't even need to draw the Lewis structure for it. Hydrocarbons. And we mentioned this a few days ago when we were talking about bond orbital models. The carbon-hydrogen bonds are polar. They have really small little dipole moments. But in every hydrocarbon, the dipole moments are perfectly symmetrical, so they always cancel out. That means hydrocarbons are always nonpolar. So in the third test, I'll probably put a molecule C20H42, tell me if it's polar or nonpolar, and I'm going to see how many people draw out the entire structure of 20 carbons bonded to 42 hydrogens and draw in the 7 dipole moment arrows and see if they cancel out. And by that time, the test will be over and you won't get to any other questions. And really what you should have just done is gone, oh, it's a hydrocarbon, it's nonpolar. Okay. So those 2 categories are easy molecular substances to predict if they're nonpolar. Any other one, you actually have a more sophisticated method to do. If I give you CO2 or BH3, they're made of 2 different elements. You have to draw the Lewis structure, predict the shape, draw the correct shape, look up the electronegativities of the atoms, subtract the electronegativities, see if the bonds are polar. If the bonds are polar, draw the dipole moment arrows on the bonds, cancel out any symmetrical set of dipole moments, and see if you have any dipole moments left over. If you don't have any left over, then that means that's a nonpolar molecule. That's always going to be symmetrical dipole moments. So this takes some work to do, CO2 or BH3, but you can still determine if it's nonpolar, and that'll be important. That's going to be one major chunk of the test next week, where I'm going to give you molecules, and I'm going to say, draw the Lewis structure, tell me the shape, and then tell me if it's polar or not, because here for test 4, you've got to be able to look at a substance and go, I wonder if it fits into the nonpolar molecular category or the polar molecular category. So if you have something that's a nonpolar molecular substance, when you cool it down into a solid and it crystallizes, it's going to have millions and millions of nonpolar molecules arranged in a repeating regular pattern. So here I've got little, like maybe a carbon dioxide molecule, and all these little carbon dioxide molecules are at the corners of the little cubes here, and they're repeating over and over and over and over again. So it's a systematic arrangement of nonpolar molecules in a repeating pattern where each lattice point, each corner of the cube is a nonpolar molecule. You wouldn't say an atom. There's a CO2 at each of those corners, not a carbon or not an oxygen. So nonpolar molecular substances have the nonpolar molecules themselves as the lattice points in the crystal. Okay. Sometimes we get confused, these nonpolar molecules, with the category over here, these macromolecular substances like boron, carbon, silicon, or like silicon dioxide. So make sure you can visualize the difference between what we're talking about right now, a nonpolar molecular substance, and then something macromolecular. Nonpolar molecular, you have millions and millions of unique molecules that make a crystal, but the molecules don't bond to each other. In a macromolecular substance, you have millions and millions of either borons or carbons or silicons, but they all covalently bond to each other. So look at the two pictures and see if that makes sense to you. This might be the most important picture in the entire thing today. Look at the macromolecular substance. This could be like maybe elemental carbon as a diamond. Here's a carbon atom. What do those black lines mean? Those are covalent bonds. So this carbon is covalently bonded to 1, 2, 3, 4 others. What's this one doing? It's covalently bonding to 1, 2, 3, 4 others. What's this one doing? Covalently bonding to 1, 2, 3, 4 others. So the very top atom in the entire diamond is connected through a whole series of covalent bonds to the atom at the very bottom. The entire crystal is covalently bonded together. That's why it's called macromolecular. It's like one giant molecule. But look at the other side. You have a diatomic molecule, 2 atoms bonded together. Here's another diatomic molecule. Are these bonded together? No, they're not. So this is a collection of millions and millions of nonpolar molecules, but this is actually one giant molecule, so it's called macromolecular. So on the left are nonpolar substances like diatomic iodine or diatomic oxygen. The right side would be an example of either diamond or sand, because those are both macromolecular. So make sure you understand the difference between those two. Right now, we're talking about this category, nonpolar molecular substances. Now, if you want to melt this, you've got to cause these diatomic molecules to separate from each other. So there must be some attractive force between them. You want to make a guess as to what the attractive force might be between these nonpolar molecules in this crystal on the left side? What do you think? No guess? London dispersion forces is correct. It's the exact same attractive force that exists between noble gas atoms, okay? So if we have a sample of a bunch of molecules together, okay, the attractive forces between the molecules are not chemical bonds. This attractive force is a London dispersion force. Now, let me use some terminology for you that we use anytime we're talking about molecular solids. When you have molecules, you can talk about the attractive forces between the molecules, or you can talk about the attractive forces within a molecule. The attractive forces within a molecule are called intramolecular forces. Intra means within, forces within a molecule. If you just focus in on the central molecule in my picture here, that's a water molecule. The water molecule is made of an O, and somehow it's attaching to 2 H's. So what you see here are the dashes between the O's and the H's. Those are intramolecular forces. What do those dashes stand for in that water molecule? What does a dash mean?
Covalent bonds.
Yeah. So whenever you have intramolecular forces, they're always just covalent bonds. They're the bonds that hold a molecule together. Is that significant for anything? Yes, it is. And it's going to be significant when we get to Unit 4. It tells you how stable or how reactive the molecule is. If those intramolecular forces, if those covalent bonds are really, really weak, the molecule will break down easily. It'll react easily. But if those covalent bonds are really, really strong, it doesn't react easily, and the molecule's stable. So that's going to be related to its chemical reactivity. So they determine how reactive a molecule is, and that's our entire topic for Unit 4. Right now, we're just talking about solids and liquids, and why would something be a solid or a liquid or gas? So that's determined by what attracts the molecules to each other. Those are called intermolecular forces. Those are the forces between molecules. And if I show them with dotted lines in the picture, these dotted lines are the intermolecular forces. So if you want to melt a crystal of ice, you've got to overcome the intermolecular forces so the water molecules can come apart from each other. So these forces between the molecules determine melting points and boiling points, and we're talking about those in this unit, so that's going to be significant. Okay. When you came to campus this week, if you had to take the freeway to go home, you may have actually gotten on the 5 freeway. It says I-5. What does that I mean in I-5?
Interstate.
What's interstate mean, do you think?
Between states.
Oh my gosh. So if Mr. Gomez left lab yesterday, and he said, I've had enough of this life, and he gets on the 5 freeway and goes north, he can drive for 28 hours, and you know where he's going to be after 28 hours? Oh, you don't know. He'll be in Canada, eh? Because if you drive 28 hours north on the I-5, it's an interstate highway. It goes from one state to another. You go from California to Oregon, Oregon to Washington, and you're going to hit the Canadian border. So inter means between. So if I talk about intermolecular forces, I mean forces between molecules, okay? And as we just discussed, these intermolecular forces for molecules are probably London dispersion forces, okay? So when you have nonpolar molecules, the attractive forces between the molecules, which I could just completely say intermolecular forces if I want, because that's what it means, are the London dispersion forces, exactly the same thing we talked about in terms of noble gases, okay? So what happens is when two nonpolar molecules approach each other, their electron clouds repel each other, the electron cloud in one molecule shifts and it gets polarized. So that molecule now has a temporary positive end and a temporary negative end. It will then pull the electron cloud of the other molecule so that the other molecule becomes polarized, having a temporary positive end and a temporary negative end. And that temporary positive end of one will attract the temporary negative end of the other. That's your London dispersion force. So this is caused by the polarization of the electron clouds in neighboring molecules. They create instantaneous or temporary dipole moments in each, and that results in the temporary positive end of one molecule attracting the temporary negative end of another. So nonpolar molecules attract the exact same way that noble gases do, by London dispersion forces. Now, what would you expect the melting points and boiling points to be for things that are nonpolar molecular? Because their attractive forces are only the London dispersion forces, which are really, really weak, we would expect it would be really easy to melt and boil them because you only have to heat them up a little bit to break the London dispersion forces. So they're going to have really low melting points and boiling points because of the weakness of the London dispersion forces. I'll use LDF to stand for London dispersion force if that's okay. Okay. So we're working through this. I want you to recognize each of the different classifications we've done so far. And let's go back for a second. Ionic matter are positive and negative ions held by strong ionic bonds. Their melting points are really high, 800 degrees, 1,000 degrees. Metallic matter is millions and millions of metal atoms attracted by metallic bonds. Metallic bonds are really strong. So metals have high melting points, 1,000 degrees, 2,000 degrees. Macromolecular matter are a bunch of nonmetals, boron, carbon, or silicon. They're held together by covalent bonds, millions and millions of atoms, all covalently bonded together in one crystal. Covalent bonds are really strong, so diamond and sand have really high melting points. But now, when we've switched to noble gases and nonpolar molecules, what holds the noble gas atoms or the nonpolar molecules together in a crystal? London dispersion forces. They're really, really weak. These guys don't have melting points of 1,000 degrees. Their melting points are negative 200 degrees. That means they melted and boiled way back when things were really, really cold. And now that you're up to 20 degrees Celsius at room temperature, they're gases, okay? In terms of water solubility, because nonpolar molecules do not have positive and negative ends, they cannot attract to the positive and negative ends of water, so they don't dissolve. I usually say low, because I can't say they don't dissolve at all. Oxygen, O2, is a nonpolar molecule, but we know oxygen can dissolve in water. That's how fish breathe, right? Fish have gills, and as they swim through the water passes through the gills, and they extract the dissolved oxygen. That's where they get their oxygen from. Oxygen doesn't dissolve very well in water, only a little bit, but it does dissolve to some small extent. So that's why I said low here as opposed to none. So these rules are generalizations, okay? In terms of electrical conductivity, the only charged particles could ever move to make electricity are ions or electrons, and there are no ions in a nonpolar molecular substance. The substance is made up of neutral molecules. And the electrons don't jump from one molecule to another. Now, Ms. Eckes would probably agree with that. You might pass electricity through them and make the electrons jump up and drop back down, but the electrons don't jump from one molecule to the next. So these things are not conductive of electricity because they have no charged particles that are mobile. Okay. The final category is also a category of molecular matter, but now it's going to be molecular matter made up of polar molecules. And let's go through the same analysis and properties for things that are fitting into the sixth and final category called polar molecular matter. So this would be anything composed of polar molecules. So if it's molecules, it has to be made of nonmetals only. So you're only going to have elements from the right side of the periodic table. Examples would be something like HBr or SO2. But it has to be molecules whose dipole moments are asymmetrical so they don't cancel out. So HBr is a polar molecule because it's linear. There's one dipole moment in it. It doesn't cancel out. It's polar. SO2's Lewis structure and from VSEPR theory predicts it's a bent molecule with a 120-degree angle. There's polar bonds in the molecule, but the two polar bonds have dipole moments that are not linear. They're 120 degrees apart, so they don't cancel out. They're asymmetrical, so they become polar. So HBr is a polar molecule because the hydrogen end of the molecule is positive, and the bromine end is negative. Sulfur dioxide is polar because I actually have this written wrong here. The sulfur end is partially positive. The oxygen end should be written as partially negative. And so the molecule has a positive and negative end to it. If you make a crystal of polar molecules like water, the crystal will have some regular repeating pattern to it. All the crystals I've shown you before always make kind of cubes that are repeated over and over again, but it's not always that way. Water actually freezes and makes little hexagonal shapes or little hexagons, but it's a regular repeating pattern that happens over and over and over again. What's at each lattice point? It's a polar molecule. There's one water molecule at each lattice point in that crystal. So the lattice points are actually the polar molecules themselves, okay? Now, what holds the water molecules together in a crystal of ice? One water molecule is not covalently bonded to another. There's got to be some intermolecular force doing that. And you might guess London dispersion forces, and that would be a good guess. Because when water molecules approach each other, they will polarize each other's electron clouds and they will cause a little positive negative attraction, which is called a London dispersion force. But there's one other thing that exists between molecules if they are polar. Polar molecules will attract with London dispersion forces, but they will also attract with a slightly different force that's called a dipole-dipole attraction. We'll try to explain that to you in a minute. But I want you to at least know at this point that non-polar molecules will only attract with London dispersion forces, but polar molecules will now attract with London dispersion forces and a new attractive force called a dipole-dipole attraction. Now, London dispersion forces are really, really weak, and dipole-dipole attractions are weak as well. So that means polar molecules are only attracted by weak forces. Therefore, it should be really easy to melt and boil them. You only need a little bit of energy. So that means their melting points and boiling points would be expected to be low. Once again, it's because the London dispersion forces are really weak, about 0.1 kilojoules per mole. And the dipole-dipole attractions are actually weak as well, but they're a little stronger than LDFs. They're about 1 kilojoule per mole. That's still 1/400th as strong as a covalent bond. So we still consider that a weak attractive force. Okay. What would you predict to be the water solubility of polar molecules? Should polar molecules dissolve in water or should they not?
They should dissolve.
Yes, because they have positive and negative ends. So that means they can be attracted by the negative and positive ends of water. So things with similar polarities will mix together and dissolve. Polar water will dissolve polar molecules. Polar water dissolves ionic substances because ionic substances are made of ions, and so the ions can be attracted to the positive and negative ends of water. In terms of electrical conductivity, a polar molecule might have a positive end and a negative end to it, but in the final analysis, a polar molecule is just a neutral molecule. There are no charged particles that exist, just neutral molecules. So with no mobile charged particles, then polar molecules would not be conductive. Okay? Now, here's a good instance where you may consider me be a liar, because you may be sitting there going, wait a second, when I go take a bath tonight, I'm not going to sit in that bathtub and then plug in my hair dryer and then put the hair dryer in the water and turn it on, because I think I will electrocute myself because I think my bath water will conduct electricity. So what's that whole bit about polar molecules like water not conducting electricity? Do you know why you electrocute yourself if you try to put your blow dryer and turn it on while you're sitting in the bathtub? Why does that water conduct electricity? Good question, huh? Answer coming in. Let's see who it is. Mr. DiFilippo, bath water contains metals. What metal is in bath water? Like iron metal, or is there gold in there? Maybe we can like filter it out and then save the gold and sell it. Aluminum, zinc. Wow, we can make aluminum cans and we can galvanize shovels and stuff. Do you really, I don't know exactly what you mean. Now, Mr. Gomez said calcium. What kind of calcium? Calcium metal? I don't know if I see metals in water. I've taken a magnifying glass before and I've looked at my water and I don't know if I see any metal in there. I know what metals look like. It's silvery and shiny, right? How do you dissolve a metal? I thought we just said yesterday that metals don't dissolve in water. Your car didn't dissolve yesterday when it rained on it, did it? Minerals, what's a mineral? Oh, ionic compounds, Mr. Gomez, there we go, they're ions. So not that Mr. DiFilippo or Mr. Gomez were wrong, but I just wanted to hear it more specifically. The water that you turn on from your tap contains ions. As the water runs over rock and eventually gets down to a reservoir, it dissolves some of the calcium ions and magnesium ions and carbonate ions that make up the rock in riverbeds. And so you have dissolved calcium and magnesium ions in your water. And so if you have dissolved ions in there, the ions can move in one direction and cause electrical conduction. So if you try to turn on your hair dryer in the bathtub, you will die, okay? Now, before Mr. DiFilippo gets too far here, okay? Mr. DiFilippo, I do not want you to go to school next week and bring a big jug and fill it up with deionized water, which has no ions in it, then take it home and pour it in your bathtub, then jump in your bathtub and take your hair dryer, plug it in and turn it on, because you'll still die. And the reason you'll die is not because deionized water conducts electricity, it doesn't, but as soon as you sit in the bathtub, unfortunately, you have a lot of salty stuff on you, and that salt from your skin immediately dissolves into the water, making it conductive, and you will electrocute yourself. So nobody try a bath with deionized water to see if I'm lying to you or not, okay? Because that just will not turn out good for anybody. Now, what is this dipole-dipole attraction we said that polar molecules exhibit? Well, you know, polar molecules have a natural positive end and a negative end. Well, if they do, then they'll attract each other naturally. They don't have to polarize their electron clouds. So a dipole-dipole attraction is just the attraction of the permanent positive end of one polar molecule to the permanent negative end of another. Okay. So HBr molecules are naturally polar. The hydrogen end is positive, the bromine end is negative. So when two HBr molecules approach each other, this second one actually spins around to face exactly like this, so that the positive end of it will face the negative end of the HBr. If these were nonpolar molecules, this one could spin around in any direction. It wouldn't have any preference. But because this already has a negative end, the positive end is drawn to it, and the attraction of that positive end of that negative end is called a dipole-dipole attraction. Now, in addition to that, the electron clouds will slightly polarize each other and make that second attractive force, which we call a London dispersion force. So there'll be two attractive forces between polar molecules, but I want you to understand what a dipole-dipole attraction is. That's just the attraction of the permanent positive end of one molecule to the permanent negative end of another. And if you think about this logically, if nonpolar molecules only attract with London dispersion forces, but polar molecules have London dispersion forces and dipole-dipole attractions, they might have a little bit higher melting points and boiling points. So because of the dipole-dipole attractions, we would imagine that polar molecules would have slightly higher melting points and boiling points than similar nonpolar molecules. And to try to point this out, I'm going to look at two different substances. One of them is named silane, the other is named phosphine. I've tried to pick two substances that have atoms that are about the same size, Their molar masses are about the same exactly, so I'm trying to make them as close together as I can, but the only difference is one will be polar, one will be nonpolar. So silane, SiH4, if you draw the Lewis structure and predict the shape, it's going to be a tetrahedron. There'll be 4 dipole moments in the molecule, but remember, 4 tetrahedral dipole moments cancel out, so that's nonpolar. Phosphine has a steric number of 4, 3 bonded hydrogens in a lone pair. That makes the shape of the molecule trigonal pyramidal. The 3 dipole moments are in a pyramid, not planar, so they don't cancel out. That's polar. So what the only difference between them is their polarity. Let's see what their actual boiling points are. Silane boils at -112, but phosphine with the extra dipole attraction holds together a little more tightly. You have to heat it up to -88 to get it to boil. Its boiling point is 24 degrees higher. It's not an incredibly huge difference, but there is a difference, and we account it to the fact that the polar molecule has that extra attractive force. That's why that happens. Okay. Now, if that were the end of the story, we'd be done for today. But one more tricky thing happens if you have polar molecules. If a polar molecule has in its formula hydrogen, and the hydrogen is either bonded to N, O, or F, there's going to be a third type of attractive force that occurs. Okay. So polar molecules that have a hydrogen in its formula bonded to either N, O, or F will have a third type of intermolecular attractive force. Now, what's significant about N, O, or F? They are the 3 take that now, try later. So N, O, or F are the 3 nonmetals in the upper right-hand corner of the periodic table, and they have the highest electronegativity of all elements. If they have the highest electronegativity, then if they bond to a hydrogen, they pull the electrons away from the hydrogen so much, the hydrogen becomes really, really positive. And when that happens, that really, really positive hydrogen will make an attraction with an N, O, or F in a neighboring molecule. That attraction is called hydrogen bonding. So hydrogen bonding is an intermolecular attraction. Okay, that was lovely. Sorry for that. Okay, if you're still there, hydrogen bonding is another intermolecular attractive force, and it's between a positive hydrogen in one molecule that's bonded to an N over F with an N over F in a. So let's see how that works. Am I muted again? How embarrassing. No, I'm not muted now. Okay, good. So let's take a look at these water molecules here. Now, these dots represent the attraction of a very positive hydrogen in this molecule here because it's bonded to an O with a very electronegative O in another molecule. Here's a hydrogen that's going to be super positive because it's bonded to an O and it's attracting to an O in a different molecule. Here's a hydrogen that's bonded to an O in this molecule, so it's super positive and it makes a hydrogen bond to an O here. So these dotted lines are the hydrogen bonds. When I get to test 3 and I ask you, where's the hydrogen bond in the picture? Like, where's Waldo? A lot of people will point to this. Oh, there's the hydrogen bond. That's the O bonded to the H. No, that's called a covalent bond, okay? The hydrogen bond is an attraction between one molecule and another molecule. So it has to be a hydrogen that's bonded to an O, N, or F with an O, N, or F in a neighboring molecule. These are the hydrogen bonds, okay? Can you think of any other molecules that would have hydrogen bonding?
Ammonia.
Perfect, NH3. And then what else? NH3 has hydrogens bonded to nitrogen. So ammonia's can hydrogen bond. N, O, or F?
HF.
HF molecules can hydrogen bond. And then there'll be a lot other molecules can do it as well, but you actually have to pay really careful attention to the way the atoms are bonded in other molecules. A molecule may have O's and H's in its formula, but if the H's aren't bonded to the O, can't do it. So it has to have the H bonded to an O, N, or F in a molecule, and if it does, then it'll be able to do hydrogen bonding with other molecules, okay? So polar molecules that can do hydrogen bonding now have a third attractive force. Besides London dispersion and dipole-dipole attractions, they have hydrogen bonding, so the extra hydrogen bonding causes their melting points and boiling points to be slightly higher than other polar molecules, if that makes sense. Okay? Now, in your everyday life or in your scientific career, hydrogen bonding actually has a fairly relevant part. Hydrogen bonding is responsible for ice being less dense than water. You know that an ice cube floats in a glass of water, right? Okay, well, what's happening there? Water molecules in the liquid phase are close together. But when you cool them down and they freeze, they form these crystals, and you might recognize that picture of the ice crystal we showed earlier today. Because the waters hydrogen bond with each other, the hydrogen bonding makes waters form in little groups of 6 that make a hexagon. And you see this right here? That's called empty space. So ice, the water molecules are actually spread further apart than they are in liquid, so ice winds up being less dense. Man, how important is that? Let's say you're a fish in Lake Superior 15,000 years ago, okay? What was happening on the Earth 15,000 years ago? Maybe 10,000 years ago.
Ice Age.
Yeah, so if it was the Ice Age, and let's say ice was like most other materials, the solid is more dense than the liquid, lakes would freeze from the bottom up because the ice would sink and would freeze from the bottom. And if you were the fish in Lake Superior, you would have been frozen, and then you would have been dead for 1,000 years with no offspring, and there'd be no more fish, okay? But because ice is less dense, the crystals float to the top, ice forms on the top of the lake, right? You know, on the top of the lake, it freezes down several feet and you can ice skate on it, right? What's below the ice? Insulated water, the fish stay alive. Wasn't for that, we may not be here, okay? Something else that hydrogen bonding does is it causes proteins to have their unique shapes. If you're a biology major, you know a protein is a series of amino acids bonded together. And the amino acid chains are long. There's thousands and thousands of amino acids in a protein. The protein's used to make hair or cell membranes, or they're used to make enzymes, which are catalysts for biological reactions. And if you ever see in your book like a picture of an enzyme or a protein, it's like this weird shape up here. What is that? Why is it all curly-Q like that? Well, it's because as you make these long chains, the amino acids have hydrogens bonded to N's and O's. And the hydrogens wind up, whoop, I didn't want to go there yet. The hydrogens wind up hydrogen bonding from one part in a protein chain to another part. And it has them stick together and they create these weird shapes. And these shapes are really, really important to create hair or to create cell membranes, or especially to create enzymes. Because enzymes are molecules that catalyze biological reactions. They make reactions go fast enough that you can actually live. If your reactions in your cells were not catalyzed, we wouldn't be able to produce enough energy and be able to stay alive. It's the weird shapes that allow that to happen. So if the protein molecules didn't hold their shape, then they wouldn't be able to catalyze reactions and biological systems would fail. If you want to see what a protein looks like if you break the hydrogen bonds, pour a glass of milk tonight and put some lemon juice in it. And you're going to break all the hydrogen bonds in the milk proteins, and you're going to see what milk looks like when all the proteins get denatured and broken apart, and I bet you won't be drinking it. The last thing that hydrogen bonding does, that's relevant to biology majors at least, is it holds the 2 strands of DNA together, right? I don't know where you were when you learned, okay, 2 strands of DNA, and they hook by their bases, and adenine hooks to thymine, and guanine hooks to cytosine, A to T, G to C, and that's what holds them together. Well, what holds them together? Adenine and thymine have a nitrogen and an oxygen, and they form hydrogen bonds with hydrogens on the opposite base. 2 hydrogen bonds hold those together. But guanine and cytosine are lined up perfectly to make 3 hydrogen bonds in a row. It's hydrogen bonding that hooks the 2 strands of DNA together. So hydrogen bonding, very important in biological systems. It'll be important in a lot of just the chemistry that we're going to do for a lot of the remaining of the semester and actually this course.